Hello everybody, welcome to the presentation. So we are discussing about the fourth module of our structural analysis 1, which is about moving load and influence lines. And I am Beena Mol, Assistant Professor from LBS College of Engineering, Kasaragod. So we are continuing our concepts. So this is our fifth video. In the first video, we saw about the basics of influence lines, its advantages, why is it needed, etc. And also we saw the concepts of influence lines of a simply supported beam when a unit load is moving from left to right, when a single concentrated load is moving from left to right. In the second video, we saw an example when a concentrated load is moving from left to right, how to draw the influence line diagrams, how to find the shear forces and bending moments from the influence line diagrams. In the third and fourth video, we saw example problems with more than one concentrated loads combined with UDL shorter than the span, and when these loads are moving from left to right, what will be the shear forces and bending moment at a section. So this is what we have learned so far, and this is our fifth video, and in this fifth video we are going to continue our concepts, and the next concept is the maximum shear force and maximum bending moment. How to find the maximum shear force on a section, how to find the maximum bending moment on the section, how to find the absolute maximum shear forces and absolute maximum bending moments for a simply supported beam. This is what we are going to study in this part, in this fifth video. So as I said earlier, in this video, we are going to learn about maximum shear forces and maximum bending moment when a simply supported beam is subjected to moving loads. Before going to this concept, let us recall how we solved problems on videos 3 and 4. We solved two problems, and for these two problems, the support conditions are simply supported beams and the loading positions were given for you. And for the given loading position, for the given section, what is the shear force and bending moment? That was what we did in the previous problems. Now, see, I repeat, what we did so far was the shear force and bending moment for a section for the given loads. Now we are going to find maximum bending moment and maximum shear force. For these problems, your position is not given. The condition given is the loads is moving either from left to right or from right to left. So the loads are moving loads. So when the loads are moving, when there is more than one concentrated load, when there is a concentrated load, when there is an UDL longer than the span, UDL shorter than the span, how will we find the maximum shear force and maximum bending moment? That is what we are going to see now. So today we will see 4 cases. Case 1 is simply supported beam subjected to single concentrated load. Case 2, simply supported beam subjected to UDL longer than the span. Case 3, simply supported beam subjected to UDL shorter than the span. And case 4, simply supported beam subjected to a train of concentrated loads. So we will move on to case 1, that is simply supported beam when it is subjected to a single concentrated load. So this is our given beam, a simply supported beam with a moving concentrated load of magnitude W. So only one concentrated load of magnitude W moving from A to B. So we know for a section, for a given section, XX, we are taking that section at C, and the distance of the section is small x from A. So we know the positive ordinate and the negative ordinate in the influence line diagram for the shear force for the section XX. So the positive ordinate is L minus x by L and the negative ordinate is x by L. So the maximum negative shear force occurs when the concentrated load is at C. See, that is the reason is that the maximum ordinate, maximum negative ordinate in the influence line diagram for shear force is at C, and maximum positive ordinate is also at C. That means we all know the shear force or bending moment. Shear force is the product of the magnitude of the load multiplied by the ordinate. So the maximum ordinate is at C. Maximum negative and positive ordinates is at C. So we will have maximum negative shear force when the concentrated load is at C, and maximum positive shear force when the concentrated load is at C. So when the concentrated load W is at C, our maximum negative shear force will be W into x by L, and maximum positive shear force will be W into L minus x by L. So maximum positive shear force and maximum negative shear force. The given simply supported beam, the influence line diagram for the shear force at a section C. See, now you can see the dotted lines. That is, the section is moved from C towards A. So when the section is moved from C towards A, what happens is the negative ordinate is reduced to 0 and the positive ordinate is increased. So how much it is increased? So your x becomes 0 there. When x becomes 0, it is L by L is equal to 1. That is, our maximum positive ordinate becomes 1 when we are moving the section from C towards A. So that means our maximum, absolute maximum positive ordinate for a simply supported beam for the shear force occur at A, and the ordinate is equal to 1. So we can recall what we have studied earlier. This ordinate is equal to 1 is nothing but the reaction, influence line diagram for the reaction at A. So that is the absolute maximum positive shear force for a simply supported beam. So now you can see the maximum value, that is absolute maximum value for the positive shear force. That is anywhere. If a section is not given for you, anywhere on the beam, the maximum shear force will occur at, maximum positive shear force will occur when the section is at A and when the load is at A. Because at A you have the maximum ordinate, W multiplied by 1, that will be our maximum positive shear force. Similarly, the maximum negative shear force, absolute maximum negative shear force. So for absolute maximum negative shear force, we are moving our section from C towards B. So when we are moving our section from C towards B, the positive shear force value becomes 0. That is, x becomes 0. So positive becomes, x becomes L. So our positive shear force value becomes 0 at B and the negative shear force value becomes 1. That is, the ordinate at B becomes 1. So this will be our condition for absolute maximum negative shear force. So maximum value of negative shear force occur when x is equal to L, that is at B, and the value of the ordinate is equal to 1. So maximum value of negative shear force is equal to W. So you can see both the positive and negative shear forces are shown in the same diagram. So when you move the section towards the A, the negative shear force becomes 0. You will get the maximum positive ordinate. And when the section is moved towards B, our positive ordinate becomes 0 and we will have the maximum negative ordinate. And remember, see the section, the values of the section, that is L minus x by L and x by L. So adding these both, this is what we have studied in our shear force and influence line diagrams, shear forces and bending moments. When we add L minus x by L and x by L, we get the value as 1. So anywhere, see from A to B, anywhere along the span, the addition of both, the summation of both positive and negative ordinate should be equal to 1. So shear force is over. So remember, we saw for a simply supported beam, when a concentrated load is moving from left to right, anywhere on the section, we will have positive or negative shear force, maximum positive or maximum negative shear force when the concentrated load is acting at the section. And the absolute maximum positive shear force is at A and absolute maximum negative shear force is at B. Now we will go on for maximum bending moment. So we know the influence line diagram for the bending moment is like this, and the ordinate, maximum ordinate is x by L into L minus x. Now, so the when there is a concentrated load, single concentrated load, the maximum positive bending moment occurs for a section when the concentrated load is at the section. So it is the value of moment is equal to W multiplied by the ordinate. So W into x by L into L minus x. Now the absolute maximum value of the positive bending moment of a simply supported beam occurs when x is equal to L by 2. That is at the middle of the section, middle of the span. Because see, at the middle of the span, we have already seen that the maximum ordinate occurs when x is equal to L by 2. We saw it in our first video. So maximum bending moment occurs when x is equal to L by 2. That is maximum ordinate. Maximum ordinate in the influence line diagram for bending moment is obtained when x is equal to L by 2 for a simply supported beam. That means the absolute maximum value is obtained by L by 2, and substituting x is equal to L by 2, we get the maximum, absolute maximum value is equal to W L by 4. So case 1 is over. That is when a simply supported beam is subjected to a unit concentrated load, what is the maximum positive shear force, what is the maximum negative shear force, what is the absolute maximum positive shear force, absolute maximum negative shear force, where do these occur, maximum bending moment and absolute maximum bending moment. Now Case 2 is simply supported beam subjected to UDL longer than the span. So uniformly distributed load, that is longer than the span. So we can see a span of length L. The UDL larger than the span is taken as W per unit length. So the total length of this load is greater than L. The influence line diagram for the shear force for the simply supported beam is the same as we see in the last sections. The maximum positive ordinate is L minus x by L and the maximum negative ordinate is x by L. Now, the maximum negative shear force is obtained when the maximum load is at the left section of C. So, the maximum negative shear force is obtained when the head of the load is at C. Now, the maximum negative shear force will be the product of the intensity of load and the area under the load. So, that is W into area under the load in the influence line diagram, that is half into base into height. It is a triangle. So, similarly, the maximum positive shear force occurs when the tail of the UDL is at C. So, when the tail of the UDL is at C, the maximum positive shear force value is, the load is W multiplied by area of the triangle under the load in the influence line diagram, that is half into base is L minus x and height is L minus x by L. Now we will see the absolute maximum positive shear force. As we saw earlier, the absolute maximum shear force, positive shear force occurs when we move the section from C to A. So the maximum ordinate becomes 1 and the maximum absolute positive shear force happens when the complete load is placed on the span. So the value for maximum positive absolute shear force at anywhere on the simply supported beam is at A and it is equal to the load multiplied by the area under the load. So we get W L by 2 and this is same for absolute maximum negative shear force also. So absolute maximum negative shear force occur at the section B. The value is equal to WL by 2. See, for both absolute maximum positive shear force, it is plus WL by 2. Absolute maximum negative shear force, it is WL by 2 minus WL by 2. Now, the influence line diagram for bending moment for the section X. So, influence line diagram is not going to change. The ordinate is x by L into L minus x for the section at C. And our maximum positive bending moment occur when the complete load is on the complete span of our beam. And the intensity is W into half into base into height. That is area under the load. W into area under the load. Now, we know that the maximum value of bending moment occurs when x is equal to L by 2. So, when x is equal to L by 2, by replacing x by L by 2, we get absolute maximum bending moment. This is absolute maximum bending moment is WL square by 8. WL square by 8. So, we saw two cases. Case 1, when a single concentrated load is moving from left to right, what about the maximum shear forces and maximum bending moment? And case 2, for the UDL larger than the span, when it is moving from left to right, what is the maximum shear force, maximum bending moments? Now we will come for case 3. Case 3 is a simply supported beam subjected to UDL shorter than the span. So, UDL is shorter than the span. We take the length of the UDL as M. This is the influence line diagram for the shear force. And for both negative and positive shear force, that is, a section is taken at C at a distance x, and when the UDL is shorter than the span, we will have two cases, two conditions. When M is the length of the load, L is the length of the beam, so, and X is the length of the section. So when M is less than X and M is greater than X. When M is greater than X, the complete load will lie on the left portion of the C, to the left of the section C. So the maximum negative shear force occurs when the head of the load is at C and the intensity is equal to the intensity of the load multiplied by the area under the load. Now, when M is less than X, the head of the load will be at C and the tail of the load will lie somewhere between A and C. And we need to find this ordinate in the influence line diagram. We take it as Y. Now we find Y by using similar triangle principles. So the maximum negative shear force is load multiplied by the area under the load in the influence line diagram. Same way, for positive shear force, when M is greater than L minus X and when M is less than L minus X. When M is greater than L minus X, the load lies on the complete span of the beam. So we get the area under the load will be a triangle, half into base into height. And case 2, when M is less than L by X, the tail lies on C and the head lies somewhere between C and B, and the ordinate under the tail is taken as Y. So our maximum positive shear force when M is less than L minus X is W into area under the load in the influence line diagram, that is area of a trapezium. We will find Y using similar triangle principles. Now we can determine maximum positive shear force. Now we will have absolute maximum positive shear force and absolute maximum negative shear force. So absolute maximum positive shear force occurs when the section is moved from C to A. The maximum ordinate is equal to 1. Now we need to find the ordinate under the head, that is Y. Now we can find the intensity of the absolute maximum shear force, that is load multiplied by the area under the load. Same way, absolute negative bending moment also. Okay. Now what will be the absolute or what will be the maximum bending moment? Listen. So we know the ordinate for the maximum bending moment is x by L into L minus x. Now this UDL is shorter than the span. So this should be placed in such a way that we should get maximum bending moment. So we do not know how it should be placed, which part of this UDL should be placed at C. Now it is our aim to find that how much portion of this UDL should be on the left of C and how much part of the UDL should be on the right part of C. Okay, so for this condition, the bending moment is the load multiplied by the area under the load. So it is Y1 and Y2, but we don't know what is Y1, what is Y2, how this UDL shorter than the span should be placed. And for this, the condition, that is, you can see the portion marked in green color, that is N. We should find what is N, so that is how much part of this UDL shorter than the span, how much part of this UDL should be placed on the left of the section and how much is the remaining portion that is to be placed on the right of the section. Now our aim is to find n. So to find n, the condition is y1 is equal to y2. When this y1 and y2, that is when these ordinates y1 and y2 are equal, we will get the maximum bending moment. Okay, so the maximum bending moment at the section is obtained when y1 is equal to y2. Now, by using similar triangle principles, we can find y1 and y2, and equating this y1 and y2, we will get a relationship between L, X, M and N. So, we are equating y1 and y2. We get X by L is equal to N by M. X is the distance of the section, L is the length of the span, M is the length of the load, N is the unknown value. So, we will be able to find N using this relation. If N is known, we will be able to find y1 and y2. We will be able to find the maximum bending moment. So, this relation is important. y1 is equal to y2, and the condition for obtaining this is X by L is equal to N by M. So, using this, find N, substitute, find y1 and y2, substitute, find the maximum bending moment. So, bending moment at a section is maximum when the load is placed such that the section divides the load in the same ratio as it divides the span. So, 3 cases are over. Now, we will go for our last case, that is case 4 is when a simply supported beam is subjected to a train of concentrated load. That is a number of loads like W1, W2, W3, W4, W5, etc. So, when any number of loads with some given distances is moving from left to right or from right to left, where will we have the maximum shear forces and the maximum bending moment? This is our last case. So, here for understanding purpose, we have taken 4 loads, 4 train of loads W1, W2, W3, W4. So, these loads are moving from A to B. Our section is taken at a distance x. So, as usual, this is our influence line diagram for the shear force. Now, the maximum negative shear force at section XX occurs when the leading load W1 is at C. So, W1 is the leading load, W4 is the trailing load. W1 is the leading load and W4 is the trailing load. So, maximum negative shear force at section X occurs when the leading load W1 is at C. So, this is the case. You can see in the diagram. So, W1 is at C and it is followed by W2, W3 and W4. So, the intensity of the negative shear force at section XX is the intensity of load multiplied by the ordinate in the influence line diagram. Okay, next is the absolute maximum negative shear force. So, we know the maximum ordinate will be at B, X by L is equal to 1, and now for absolute maximum negative shear force, the head of the load W1 should be at B. Now, intensity you multiply by the intensity of load by the ordinate in the shear force diagram. Similarly, for the positive shear forces. So, for positive shear force, the tail or the trailing load should be at C. Trailing load should be at C. And the other loads as usual, how much the distance is given for you. And the intensity is obtained by multiplying the intensity of load multiplied by the ordinates. And the maximum positive absolute shear force is obtained when the section is taken at A and when the trailing load W4 is at A and the other loads followed by it. Now the bending moment. So let us remember, when the UDL is shorter than the span, our condition is y1 is equal to y2, x by L is equal to n by m. Remember that. Here we have another conditions. When there are train of loads, we will have another conditions. See, first case, when W1, W2, W3, W4, etc. we have to divide this into two portions. That is, one set of load acting in the portion AC and another set of load acting in the portion CB. Now, see, we have two sets of loads. Let R1, we take the resultant of the loads acting on the left of the section as R1 and the resultant of the loads acting on the right of the section as R2. So, R1 and R2. R1 resultant at the left of the section, R1 resultant of the loads at the left of the section, R2 resultant of loads at the right of the section. Now, the condition for maximum bending moment is, so again, see, we take bending moment, differentiate it, we will get the condition. I am not giving you the derivation, just giving you the condition. Exam point of view, this is needed for us. So, the condition for maximum bending moment is R1 by X is equal to R2 by L minus X. R1 divided by X, that is the distance of the section. R1 divided by X equal to R2 by the other part of the section, distance of other part of the section, L minus X. Now, we know the maximum ordinate for the simply supported beam is when X is equal to L by 2. Now, when we substitute X equal to L by 2, we get R1 is equal to R2. Now, what is R1 and what is R2? R1 is the resultant of all the forces we have chosen to the left of the section, and R2 is the resultant of all the forces we have chosen to the right of the section. See, these loads, when a number of loads are given for you, these loads are taken almost equal. That means if some 5 loads are given for you, you can take 3 plus 2. So, the magnitude should be almost equal. If this is 100, this should be 100, or if this is 110, this should be some 100. It should be approximately equal, this R1 and R2. But for the maximum bending moment, the condition is R1 is equal to R2. That means both the resultants should be equal. But this is not possible if you are provided with different varying loads, varying concentrated, that means different concentrated loads. Suppose if you are given with some 6 concentrated loads, each with weight 50. The concentrated load is 50, 50, 50, 50, 50, 50, 50. Then it's okay. R1 will be equal to R2. And we can take this condition, R1 by X is equal to R2 by L minus X. Suppose if 6 loads are given for you, 6 concentrated loads are given for you, 40, 30, 20, 10, etc. It's not possible. So, we have come to a conclusion that it is assumed that R1 is not always equal to R2. So, it is assumed that bending moment is maximum when one of the load is at section. So, if you have 6 loads, any one load should act at the section. That is at the maximum ordinate. Any one load among this 6 loads. If 4 loads are given for you, among this 4 loads, any one load should act at the section. Now it is our aim is to determine this load. Which load should act at the section? Okay. So for that, we will take R is the resultant of all the loads. If 4 loads are given for you, R is the resultant of all the 4 loads. So this R will act at some point, right? When W1, W2, W3, W4, R1 will act at some point. Now see which load is closer to R. That is, the distance of which load is closer to R. Okay, now for example, for this case, R is the resultant of W1, W2, W3 and W4, and R is closer to W2. So we will take the distance of this resultant R from A as Z, and the distance between the resultant and the load closer to the resultant, that is W2. So the distance between R and W2 as small d. Now after doing this, we will find the moment, and differentiating, we will get a relationship between Z, D, X and L. That is the condition for maximum bending moment at any section when a train of loads is given for you. The condition is Z plus D is equal to L by 2 plus D by 2. So what is Z plus D? That is X. X is equal to L by 2 plus D by 2. This is the condition. So when will this occur? This will occur under one of the loads when the resultant of all the loads and the loads under consideration, that is W2, are equidistant from the center of the beam. Okay? So you can see Z plus D, that is, a section is shown. So Z plus D is shown for you. Z plus D, that is equal to L by 2 plus D by 2. Z plus D is equal to L by 2 plus D by 2. So this will occur under one of the loads when the resultant of all the loads and the load under considerations are equidistant from the center of the beam. So listen, when a problem is given for you, such problem, when a train of loads is given for you, find the resultant, find the load closer to the resultant. So take the distance of the resultant from A as Z, take the distance between the R and W2 as D. Now apply the condition so that we will be able to find the maximum bending moment when a train of loads acts on when a train of load is moving from A to B in a simply supported beam. Thank you. So what we have studied today is case 1, when a simply supported load is given and a concentrated load is single concentrated load is moving from A to B. What is the maximum positive shear force, maximum negative shear force? What is the absolute maximum positive shear force, absolute maximum negative shear force, maximum bending moment, absolute maximum bending moment? 6 things. Then case 2, for a simply supported beam subjected to UDL moving from left to right, and when the UDL is larger than the span, what is the maximum negative shear force at a section, maximum positive shear force at a section, absolute maximum positive shear force, absolute maximum negative shear force, maximum bending moment, absolute maximum bending moment. Case 3, when a simply supported beam is subjected to a moving load, moving UDL shorter than the span, when it is moving from left to right, what is the maximum negative shear force? We have 2 cases. When M is less than Z, M is greater than Z. Case 2, next is maximum positive shear force, 2 conditions. Absolute maximum positive shear force, absolute maximum negative shear force, maximum bending moment. So the condition is X by L is equal to N by M. Then case 4, when a train of loads is moving from left to right. So when a train of load is moving from left to right, what is the maximum positive shear force? What is the maximum negative shear force? Absolute maximum positive shear force, absolute maximum negative shear force. What is the bending moment at the section? What is the condition for obtaining the maximum bending moment at a section? So these are the things what we have studied in today's class. See, with this concept you can easily solve the problems. Now you can go on solving the problems. You will easily understand how to solve the problems. So we will solve a few problems in tomorrow or day after tomorrow. So hope you all understood, and if you have any doubts you can comment on the section or you can call me. Thank you. Thank you once again.